All right, we're about to dive into one of the most iconic charts in all of science. We're going to unlock a secret that was hiding in plain sight for, get this, over 100 years.
You've all seen the periodic table, right? It's literally a masterpiece, like a roadmap to, well, everything. But have you ever really looked at its shape? It's kind of weird, isn't it? A little random looking. But what if it's not random at all? What if there's a hidden code that explains exactly why it's shaped that way?
Seriously, why this shape? Why do the rows, we call them periods, have this very specific number of elements? 2, then 8, then 8 again, then 18, another 18, and then 32. I mean, it's a pattern, sure, but it's not exactly simple. What is the rule? What's going on here?
You know, that exact question stumped scientists for more than 100 years. Ever since Mendeleev first came up with his table, nobody could find one single, clean, mathematical formula to predict that pattern, that 2, 8, 8, 18 pattern. It just existed. People accepted it. That is, until very recently.
And that brings us to 2017. A researcher named Jean-Claude Perez published a paper that, well, it finally cracked the code. He found a single equation that could predict the whole thing. And the crazy part? It had been overlooked for decades.
And this is it. He called it the generic equation of Mendeleev. And when you first see it, the most shocking thing is just how simple it looks. Right? For something as complex as the entire periodic table, you'd expect some monster equation. But no, this thing is elegant. It's a simple key to a really complex law.
Okay, let's break this down real quick so you can see how it works. It's actually not scary at all. So P is just the row number you're on. Simple. C of P is the answer we're looking for, the number of elements in that row. And that int part, that just means you only pay attention to the whole number. So if you get 2.5, you just use 2. That's it. See? Easy. All right, let's walk through it together. Step by step, it's like a recipe. First, you take the row number, P. Step 2, add 2 to it. Step 3, divide that by 2. Then, step 4, remember to just take the whole number. Step 5, you square that number. And the final step, you multiply the whole thing by 2. That's it. That's the entire magic trick. Okay, enough talk. Let's actually put this thing to the test. Let's try it for period 4. So P is 4. Okay, follow along. We take 4, we add 2, that's 6. Divide by 2, we get 3. The whole number part of 3 is still 3. Then we square it, so 3 times 3 is 9. And finally, we multiply by 2, which gives us 18. Go ahead, look at any periodic table you can find. Row 4 has exactly 18 elements. It works. It actually works perfectly.
And check this out. It wasn't just a lucky guess. Look at this table. For row 1, the formula spits out 2. And, yep, that's right. For rows 2 and 3, it predicts 8. Spot on. For 4 and 5, it gives us 18. Perfect again. And for row 6, it says 32. It's a perfect match. Every single time. This is that aha moment. The code is real.
Okay, so the formula works. That's amazing. But here's where things get even cooler. Perez's discovery doesn't just explain the flat chart we're all used to. Nope. It lets us see the periodic table in a whole new dimension. And this is where it just gets beautiful. The equation lets us take that familiar flat table on the left and transform it into these incredible 3D crystal-like shapes you see on the right. It's telling us that the elements aren't meant to be in a flat grid. They have a deeper, more symmetrical, more geometric reality. And these diamond-like models, they show us symmetries that were totally hidden in the 2D version. You can see they're made of 4 pyramids, all connected together. And as you add elements, it just grows perfectly, symmetrically from the center. And here's a big one. You see those 2 rows that are always floating at the bottom of the chart, the lanthanides and actinides? Well, in this model, they finally get put back into the main structure, right where they're supposed to be. And this formula isn't just about explaining what we already know. It's predictive. You can actually plug in bigger and bigger numbers for P, like row 8 or 9 or even higher, and it will tell you how many elements should be in those rows. It's basically a blueprint for elements that we haven't even discovered or created yet. How cool is that? So, okay, we've got this beautiful math, this incredible pattern. But the biggest question of all is still out there. Why does it work? Is this just some cool numerical coincidence? Or is there a much deeper reason rooted in physics? Well, that's what we're digging into next. The quantum blueprint. I mean, think about it. Is this just a clever party trick with numbers? Or did Perez's equation accidentally tap into the fundamental laws of the universe that actually build the elements?
To get that answer, we have to talk for a second about something called quantum numbers. Don't worry, it's not as scary as it sounds. Just think of it like this. Every single electron in an atom has its own unique address. This address is made up of 4 quantum numbers. And these numbers basically tell you everything about that electron, its energy, the shape of its path, where it is, the whole deal. It all comes from the rules of quantum physics.
And here it is, the grand finale. Perez showed that his formula is not a coincidence. Not at all. It can actually be rewritten to include 2 of those quantum numbers we just talked about. This means the equation isn't just describing the table. It's a direct reflection of the quantum rules that build the atoms themselves. It's the blueprint.
So, let's just let that sink in. The big takeaway is this. That strange, beautiful, and for 100 years mysterious shape of the periodic table, it's not random at all. It is a direct result of the invisible quantum rules that tell electrons where to go inside an atom. The giant chart we see is a perfect reflection of the tiny, tiny world inside.
And that leaves us with this final thought, which comes from a Nikola Tesla quote that Perez actually put in his own paper. The scientific man does not aim at an immediate result. His work is like that of the planter, for the future. Think about that. A discovery in 2017 solves a puzzle from the 1860s, using physics that was figured out in the 1920s. It's just a beautiful reminder that sometimes the seeds of a great idea can take a very, very long time to finally bloom.